Hi, and welcome to another lecture in this course. And what we're looking today is the Dirac delta functions and the impulse response. And this is in the Laplace transform chapter, so that's the context in which we're looking at this. Now you can get this book for this course at this URL or this URL, and you can browse it online, or you can get a cheap paperback one. All right. So otherwise, it's free, of course. All right. So let's get into this. So one way to study, if we have some physical system and we want to figure out what it does, what we could do is, we could poke it and see what it does, right? So we could send, a short pulse as input and see what pops out, right? And so what do we mean by a short pulse? This sort of poke that we have. Well, the simplest version of this is just a rectangular pulse. So some function that is just zero, it keeps being zero, and at some point it goes to some value, and then it's zero again, right? So this is called a rectangular pulse. And so it's zero, all the way up to some a, then between a and b, it's m, and then from b onwards, it's zero again, right? So in this case, a was half, b was 1, so between half and 1, or something different from 0, and what we are is m equals 2, so we're 2 between there. Okay. Now we can write this, this function phi, this pulse, using the unit step function. So the step function is just a function that's 0 until the origin, and then it's 1 further on, right? That's the Heaviside function. That's what we denote by u, right? And the reason why we do this, we write it this way, is so that we can apply the Laplace transform in an easy way. And so, okay, so let's Laplace transform phi, right? So we write out what it is, and we just apply, look at the table. So in the table, for example, you can see that's what the Laplace transform of the shifted step function is, right? So you just plug that in, and this is what pops out. All right, now really we're going to be looking at sort of a special kind of a pulse. So first, for simplicity, let's just start at 0 at the origin. So we're going to start right here rather than a bit later. And we're going to go up to, instead of just some random m, we're going to go up to 1 over b. And the reason why we do that is so that the integral of this function is 1. It's basically so that the area under this curve is 1, right? So it's it's a rectangle, and its width is b, and its height is 1 over b. So it's the area is 1, right? And really, we can think of this as sort of a pulse of unit mass or unit right? It's we want, no matter what b is, we want the same amount of in some sense, right? From this pulse, the same kind of a poke, right? All right. So for this unit mass pulse, what we're getting is, well, if I plug in, a equals 0 and m is 1 over b into the previous computation, we get this, right? All right, so now where the delta function is going to come about is by taking b to 0. So we're going to take some sort of a limit here in this, right? So if you look at this, try to figure out what it is that we're getting. You have to do a little bit of computation, but you can find that as b goes to 0, what we're getting is 1, right? So we're going to get this delta function, this object that we're going to get is something whose Laplace transform is 1, right? The function 1, which is the Laplace transform that we haven't seen before. It's a Laplace transform, for example, it doesn't go to 0, as s goes to infinity, just constant 1, right? Okay, now there's a little hitch in all this, is that there is no such delta function. It doesn't exist, or at least it's not a function. It exists as some sort of a thing, sometimes called a generalized function, sometimes called a measure, but it's not really a function, and we'll see why in just a moment. But yeah, there's no such function, but it's good enough for us. We're gonna basically assume it's as if it were a function, and that works. It is, can make sense of that object, but we're gonna just, pretend that the function is just a function that you cannot really evaluate. You cannot, namely, you cannot say what is delta at 0. It doesn't make sense. Okay. Now, if it were a function, so if there was such a delta, what we would get is this formula, which is really really useful. So that's one way that people, and then we're gonna see why that's true. But it's one way that people think of what a delta function is. It's the thing that if I multiply another f with it, so some other continuous f, multiplied by delta, and I take the integral over everything, over the entire real line, or essentially any interval that contains 0, then what I'm gonna get is the value of the function at 0. It kind of, the delta function can pick out the value of a function, right? So it's, and essentially there's no actual function that can do that, but the delta function, again, not quite a function, but it's an object that will be perfectly fine doing, and you can make all this rigorous. It's it's basically something that you can put under an integral. You cannot evaluate it, but if you put it under integral, it has this property. That's the main property that the delta function has, right? And so, like here's another another computation with the delta function. It's something you can figure out when you are when a certain point is in an interval, right? So if I integrate the delta function over any interval c to d, right? It's basically going to give us 1 if the origin, if 0, is in this interval from c to d, and it's going to give us 0 otherwise, right? That's another another way of seeing what the delta function does, right? So it can sort of determine intervals. It can it can evaluate functions. Okay, now here maybe just a small note. We're really thinking of the main thing is that we're thinking of the endpoints as really the interval seeing the endpoints. So maybe you can think of these as limits from the outside. So just that so that you get or less than or equal to, and really that we have this closed interval, right? It's less than or equal to, not less than. Okay. All right. Now, so really, what the delta is, right? Think of these pulses, right? They had some sort of oomph, right? And as b became smaller, this oomph was getting closer and closer to the origin, right? All this mass. So delta is the one where this rectangle of area 1 is above the 0, right? Which sort of does make sense, right? It's sort of an infinitely thin rectangle of some non-zero. So it's like a rectangle of side 0 and some really it's really really tall, so that its area is 1, right? It doesn't make sense, but that's what it is. I mean, that's why there is no function that does this. So you can think of it as sort of being, it's the delta is 0 everywhere except the origin, and it's extremely infinite. It's not just infinite; it is very infinite at t equals 0. Whatever that means. It's not a function again, so you don't really want to think of evaluating it. All right, but it is a limit in some sense of these pulses of decreasing length. So as b goes to 0, and whose integral is 1, right? So it's these pulses phi, right? And so let's look at to why it's work, right? So it's for small b, be positive, but very, very small, and some continuous f, right? Let's take this interval, right? Let's see why this is f at 0. Well, actually, in the limit as b goes to 0. Okay. Well, what is phi? Phi is some function that's basically 0, except on the interval from 0 to b. If we're on 0 to b, the phi is 1, and it's 0 otherwise. So basically, I could just integrate from uh, from 0 to b. Sorry, it's not 1, it's 1 over b, right? So phi is 1 over b there, so that's why I have 1 over b, right? But it's 0 otherwise. So really, this integral, that's just this integral, right? Okay, now f is continuous, and so as long as b is really small, right? If maybe if I draw this over here, if this is my axis, right? This is the t-axis, right? And so f is continuous, but if b is really, really small, right? Then in this interval, I mean, f is not constant, but it's kind of nearly constant. It's very close to its value at 0, right? 0 is over here, right? So it's not quite the same value over here everywhere, but it's very close. So also its integral is going to be, well, not equal, but close to the integral of just the constant, whatever f is at 0, right? And, well, if you take this integral, it's just an integral of a constant. That's just f at 0, right? So for a very small b, this side is very close to this side. So, since we're taking the limit as b goes to 0, we get that, with the phi replaced by delta in the limit, this side will become f of 0, right? So again, it's not a function, but it's something we can integrate, right? So it's something that we can put under the integral, and you don't really want to think of it too much outside the integral, right? Or at least not as a function, right? As sort of this generalized function. You don't want to sort of it's not something that gives you values, right? Okay. Now we can also shift the delta, and it's just if I shift it by a, all it does it changes which point it picks out. So if I shift it by a, it evaluates the function at a rather than at 0, right? That's just by change of variables. So we can evaluate the function at any point that we please, right? You can also it's symmetric. So delta of a minus t is the same as delta of t minus a. So we can also put it under the convolution. Again, our convolution is from 0 to t. Really, really we're thinking of minus infinity to infinity, and we're thinking that our functions are all 0 for negative t, right? But anyway, so we can put in. So this is for positive t, right? We can put in. We can convolve with delta. So we can put a delta into the convolution formula, and we're just gonna get the f back, right? So if we convolve with delta, we get f back. It's actually going to be a very useful property. Seems maybe not useful at first. It seems like we're just making things more complicated, but it's going to end up being quite useful. All right. So let's compute the Laplace transform. Well, I mean, again, something that we can put under the integral. So we can easily compute the Laplace transform because the Laplace transform of anything is just given by an integral, right? So we, put it in, and what the delta function does, it picks out the value of the function. So the function, in this case, is e to the minus st, right? For some fixed. Well, as far as the integral is concerned, s is fixed, right? And so, and what the delta function does when we evaluate this integral, it just picks out the value of the function at t equals a, right? So you can see that e to the minus st becomes e to the minus as, right? The t becomes the a. I guess I flipped the order. It, so it looks more, it was more standard to put a constant in front, right? But essentially all that happened is that t became an a, right? And in particular, if if a is 0, we just get 1, and we saw that before, right? Okay, now so let's do a simple example. For example, we can now take inverse Laplace transforms of some improper rational function, right? For example, s plus 1 divided by s, right? We can find what the inverse Laplace transform is in terms of the delta function. It does not have, s plus 1 over s does not have an inverse Laplace transform as a exponential type function. That doesn't exist. But with the delta function, we do get an inverse Laplace transform. So we just rewrite s plus 1 over s as 1 plus 1 over s, use linearity, and then we just look up in the table and we just computed that the Laplace transform of the delta is 1, right? So the inverse Laplace transform of 1 is the delta. Okay. All right. Now, let's get this remark. So if we take a look at sort of the standard jump discontinuity, it's the Heaviside function. So shifted Heaviside function at a. So it's a function that's 0 until a and then 1 from then on, right? So it jumps. And so its Laplace transform is e to the minus as divided by s. Now, if this thing had a derivative, right? And it does, well, it sort of does at most points, right? At most points, it's just constant, right? Except at that jump discontinuity. I mean, it's like, what's the slope of that function? And it doesn't seem to even make sense, as a question. What the slope of that function? Somehow very infinite, right? I mean, you have to jump, right? So if you try to look at the secant line, right? I mean, you're just gonna get that the derivative goes to infinity somehow. But think about what happens with Laplace transform when you take a derivative is that you multiply by s. Now, if you take this guy e to the minus as divided by s multiplied by s, you get e to the minus as, and that's the Laplace transform of the delta function that's shifted by a. Moreover, we can also have this for integral. If I integrate the delta function from 0 to t, right? Here tau is just some dummy variable. What I will get is the Heaviside function shifted at a, right? Because I get basically until I get to it's this delta function just picks out was a in the interval from 0 to t, right? And so until as t grows, a is some positive number, right? And so as t grows, first we don't get this tau minus a. When does that become 0, right? And so as once we get to a, suddenly tau minus a becomes 0 for some tau in the interval from 0 to t, right? And so then this integral becomes 1, right? And so so that's what it is. That's what the formula is. And so, well, so that looks like we think of fundamental theorem of calculus, right? It's both of these are basically saying that the derivative of the Heaviside function, if the Heaviside function is the delta function, right? So we have we kind of figured out how to differentiate a jump discontinuity, right? Um, we just get we just get a delta function, right? And that's actually very very useful. You know this sort of computation is used all the time, especially in engineering and in the applied sciences, but even in pure math. So now you know how to differentiate something that before you thought was not differentiable. Now you say, well, what about if I had a corner? Well, corner, that's easy to differentiate in some sense. If I have something that's a zero everywhere and then starts being slope one, so it has a corner. Well, that would be the derivative of that would be the delta the Heaviside function, right? It'd be you get a jump discontinuity, right? You get something that's it has some derivative over here, and then suddenly it has some other derivative elsewhere, right? So um, and this can keep going as well, right? We can take the derivative of the delta function, but let's not worry about that. You can. Let's just say that. But it's the basically one way of thinking about the delta function. It is the derivative of the Heaviside function. All right. So again, for a differential equation where L is some linear differential operator, constant coefficient differential operator. So you have L of x is equal to some f. If we're thinking of f as the input and x as the output, that's what we're going to be looking at here. So it's that's what we're trying to say in the beginning. We're trying to poke this system, figure out what it does for all different inputs. We just need to really figure out the so-called impulse response. So we're gonna look at what it does if we poke it, right? And the simplest sort of poke is the delta function, right? So we're gonna solve this differential equation, and that's gonna be the impulse response, right? So okay, so and as far as the initial condition, we're just gonna set them to 0, right? So let's try to find the impulse response for this this differential equation, right? So for this operator, right? So it's the solution to this differential equation, right? But again, it in some sense it doesn't make sense, but it makes sense from a Laplace transform sort of way, right? So we're going to use Laplace transform to solve it, right? So if I Laplace transform everything over here, it makes perfect sense. I get this, algebraic equation, and I can solve that for capital X. So now I have my, the Laplace transform of my solution is over here, right? And I can do inverse Laplace transform that just, basically you just look into the table, right? You're gonna get that it's sine. Well, I guess in the table you would have some omega on the top, so divide that. So this is the inverse Laplace transform, and again, this is only for t positive, right? So that's the solution. That's the impulse response. That's the solution to this guy. This fairly nice function. Now you might as well, but did we get this guy, right? Yeah, this guy seems easy, right? X of 0 is 0, but is x prime of 0 really 0? Yeah, I mean, it almost seems like this might be a tricky question. I mean, for this formula, it doesn't seem to be, right? I mean, sine. Let's just suppose that omega is just 1 for simplicity. Sine. You just have sine of t. The derivative is cosine, right? And so cosine at 0 is 1. It doesn't seem to be 0. But that's really because we're thinking of it wrong. I mean, this function. I mean, it's really 0 all the way up to t equals 0. It's not really the sign of t, right? It's 0 and then sine of t, or t positive, right? So really there is a corner, right? It's 0. So, x prime is 0 for all negative t, right? And then it has a corner, right? The corner, basically gives us a jump discontinuity. So x prime is going to be 0, and then it's, let's suppose that omega is 1, then it's going to be 1, right? From the, if we approach from the right-hand side, right? So, okay, so x prime is a jump discontinuity. And then, the x double prime, well, it's going to give us our delta function, right? Because we're going to differentiate a jump discontinuity, right? Now, really what we have in terms of this, because it sort of doesn't make sense to evaluate. So really what you should think of it as is, that it's x prime of, the limit, it's really the limit of x prime from the left, right? So, x prime 0 minus, right? Which is the limit from as t goes up towards 0 x prime. That's really the way to think about it. But, it's really important that, that it's not sine, it's fine for positive t, 0 for negative t, or undefined for negative t, right? Okay. Now, we know that the solution to this equation for any continuous f, was given by this formula. Right? Now, so that's what we saw in the convolution section, right? But this guy, that is the impulse response. So the solution for an arbitrary input is convolution with the impulse response. That's really where, where impulse response becomes important, right? Or, well, where impulse response, that's why we can come up with the the solution for any input once we know the impulse response. So, we take our system, we poke it with a stick, we figure out the impulse response, and from then we can get the output for any input, right? Because we know this function, right? So why? Well, there's a there's a way of thinking about this. Well, so first, suppose that f and h are two functions that are 0 for negative t, right? And and for simplicity, think about them. Suppose that they are actually differentiable. Everything's nice. They're nice functions, right? And I look at their convolution and I try to differentiate twice. Now, that's what I'm doing. I'm differentiating this formula. Now, it's, you really want to think of, you can think of this 0 and t as really minus infinity to infinity. But it's, really the integral only falls on that, and that's the convolution that we have with Laplace transform. So there really are some, if we do this, there are going to be some boundary terms, but they're all going to be 0 because these functions are 0, on all negative t, and let's just assume even their derivatives are 0 on for all negative t, right? So you're actually going to get this formula, and that you want to think of it as the integral from minus infinity to infinity. That's maybe the better way of thinking about it than if you apply the standard rule for differentiating under the integral. That's all that happens is that you're differentiating this t doesn't really matter. It's this t, right? And so, you're not differentiating the f, you're differentiating the h, right? That's something that's a very standard computation with convolution, is that convolution, you can think of the derivative of a convolution. It really falls on one of the two convolved functions, right? And so, it's, if we have one that we know something about the derivatives of that function, which in this case is going to be h, we can have the derivatives fall on h, right? And so we can see that the second derivative of f convolved with h is f convolved with the second derivative of h, right? So suppose that h is the impulse response. Then what we have is, well, we start with f. That's the same thing as convolving f with delta function, right? That's what we said. Well, it's the impulse response. So we get, right, it's the solution of this thing when the right-hand side is delta, right? So delta, that's just what this is, right? So we're, that's all it is. We're looking at f, f convolved with this guy, and so all right. So I will just use the linearity of the integral, right? So we can really just convolve here, and then over can just use that f convolved is h double prime is f convolved is h double prime. So we get this thing, right? And that's just f. Okay. So what we have is that the convolution with h is just the solution here, right? So it just follows from this formula, right? And the fact that well, actually two facts, right? That f convolves with the delta function is f, and the delta function has this formula, right? So okay, and the same thing worked. I mean, it didn't really have to be this particular equation. It could be any constant coefficient linear equation. Same idea works. Now, another remark is that this little h. There's a reason why we call it little h, because it's its Laplace transform is that capital H, that the transfer function that we talked about before, right? So it really, it's all this is related, right? So the inverse Laplace transform of the transfer function is the impulse response. Okay, so now we've come full circle. All right, well, let's look at a completely different application of the delta function, just to see that delta functions are useful in other places, not just impulse response. So, for example, representing point loads on a beam. So if we're bending a beam, we have a beam of length L, right? And it's being bent. There's a mass, and we're thinking of the mass as acting in a single point, right? Don't worry about this yet. So it's there's a force F at a single point pointing down, and the beam is simply supported. So it just it's lying at these 2 points, or hinged or whatever, but it's so it can't move up and down it, but it can bend at those points, and it's basically like a bridge, and we have some heavy load at one point, and we want to figure out, well, how did the beam deflect, right? So um, all right, so the differential equation for this, don't worry about y, is this guy. So y is the deflection, right? So at any particular point, y is how far is the beam deflected, right? So negative y is deflected downward. In this case, yeah, it's going to be down because the force is going down. Okay, so so that's the Euler-Bernoulli equation. Now, these E and I are just some constants, and this is the force at any particular x on this beam, right? So in our case, it's going down, so it's minus f, right? And because it's at a single point, right? It's zero everywhere else. At a single point, it's really the delta function, right? And notice that now we're putting x in there. It's not in the t variable. It's now in the x variable. It's just the name. That's all it is, right? So, and here, another thing to notice is that this is the fourth order equation, right? It's a very simple fourth order equation, right? And you can solve this easily, right? You just integrate 4 times. All right, so we have this this equation. We also have from the from the support simply at the ends. It's let's again not worry about y, but these are the endpoint conditions on here. Really, that y at 0 is 0 and y at L is 0. Well, those are obvious. I'm fixing the beam at the endpoints, and then well, we get two more, and it's and because um, uh, because these are simply supported, that's just what it is. It's that y double prime is 0. It's it can have some slope, but it's at those endpoints it's not going to have any curvature basically, right? Okay, so let's do a simple example of this sort of computation. So both for simplicity, the length is 2, so L is 2, right? We're gonna put the mass at the center, which is gonna be at 1, and we're gonna make these constant E and I. Don't worry about what they are. For the point of this exercise, right? We're just interested in the math, right? Let's just make them 1. As opposed to force is 1, right? So the equation is this, right? Let's not worry about the physics of it, right? This is this equation. So we have minus delta of x minus 1 on the right hand side, and then these boundary conditions on here, right? Okay, so let's just solve, right? I mean, it's we're doing Laplace. Let's use Laplace, but now we're taking Laplace in x rather than t because there is no t in here. So that's one reason. But yeah, you can take Laplace in any variable. Again, it's also all just names, right? So you get perfectly fine to take it in for x instead of t, right? We're still gonna call the transformed variable s. So write capital Y as usual for the Laplace transform of little y, right? And we get just the fourth order derivative. Yeah, so we get this annoying expression, right? And then we have a 1, so I have e to the minus s, right? 1 times s, and there's the minus sign, right? So we get minus e to the minus s, right? Okay, we can we have this guy and this guy, right? Will give us they appear here and here, so we can just those are 0, so we can remove those. The other guy, well, we don't know them. Let's give them names. Let's call them C1 and C2 for simplicity, right? So that we don't have to keep writing these expressions. And we solve for capital Y, which is basically just moving those two terms to the right and then dividing by s to the 4th, right? So there's your solution. Well, not quite. I mean, we still haven't used these two these two conditions. Now we well also we haven't taken the inverse Laplace transform yet. Okay, so let's take the inverse Laplace transform, and it's just second shifting property to take the transform here. But yeah, that's just you look it up in the tables, and that's what you get, right? All right, so that's what we got before. So now we still need to apply this these two guys, right? So we have well, first one is simple. You just plug in x equals 2, right? And I get this, it's supposed to be 0, right? And so, so I have this, this is equal to 0, right? Now, when x is near 2, this guy, the Heaviside function, right? It's shifted at 1, so it has a disjunct discontinuity at 1. But once x is all the way at 2, it's just 1, right? So if we're we could just replace when we're taking the derivative of y, we could just replace because we're gonna be plugging in x equals 2. Near there, this function is just 1, right? So we can replace this with a 1, right? And that's, so now it's just a polynomial. It's easy to take the second derivative. You take that and plug in 2, and that's what you get, right? So leaving out a little bit, but that's exercise for the for the intrepid reader or listener or viewer, I guess. So okay, so if we simplify, we get that zeros here, and you solve, right? So you can easily solve for C2, right? Over here, that's be 1/2. Once you know that C2 is 1/2, you plug that into this equation, right? Then you get that C1 is -1/4. And so our solution, our overall solution for the uh, for the beam, right? This is the shape of the beam between 0 and 2, right? It has this formula, right? So this is another application of the delta function. All right, so something that wasn't quite, just so that we have, this delta function is very useful, right? So just so that we have other uses of it. Okay, now, so next time what we're gonna look at, we're gonna, we're gonna skip 6.5. We're gonna move to chapter 7. We're gonna start looking at power series. All right, so see you then.